Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a look at another one of our STM32 basics videos. With a bunch of the videos coming up, we're going to be looking at a bunch of different things that we can do with timers. They're possibly one of the most versatile peripherals in the STM32 devices. So what we're going to do today is take a bit of a look at a system that's going to allow us to a bit more easily dynamically manage the timers and be able to determine which ones are available, which ones have certain features, so whether they're 16-bit or 32-bit timers, things like that, whether they have support for rotary encoders. So we're basically going to look at taking a bit of a look at writing a class that's going to allow us to do dynamic timer management. And then shortly after the end of this stream, I'm going to be starting another stream where we'll be getting into the first actual uses of the timers themselves. In that stream, we're going to be having a bit of a look at using timers to trigger a periodic interrupt at specific points in time, whether we want that to be something that happens continuously or just a certain amount of times. But in order to prepare us for that stream, as well as some of the ones coming up after that, we're during this one going to be looking at getting a singleton class written that allows us to do the dynamic timer management effectively. Like I said, check what timers are available and what particular features and things we're got for each of the timers. Today we're also going to be using the STM32F411 Nucleo device that we used during the last STM32 basics stream or video, which is this guy right here. And in this one, we actually have 8 different timers that we can use, 2 of which are 32-bit and 6 which are 16-bit. And 5 of which have encoder support. So let's jump back to this screen here. So this is the code where we left off after doing the external interrupts video last time. And we're basically going to be adding on to this one so that we're slowly building up a variety of different drivers and utilities and things that we can use moving forward. And much like the previous video, the code from this one will be available on GitHub after the end of probably the next stream, because I'm going to do sort of 2 streams in a row, as I mentioned. So first things first, we'll get stuck into it. We'll jump into our QA drivers folder, and we're going to get a couple of files created so that we can pop the timer manager in there. So just going to call this one QAD timer mgr.hpp, and we'll create a CPP file for that one as well. And if there is specific peripherals or bits of the STM32 that you would like us to take a look at, or things that you wanted us to go a bit more in depth with, definitely feel free to leave a comment either on Twitch or YouTube or on our subreddit /ones and zeros. More than happy to try and help out there where we can. Try and share some of the enjoyment that I get out of doing this sort of stuff with other people. So just going to copy and paste our header in there from our XD header file, and I'll get this all set up for what we're going to be doing here. And the benefit of doing it this way also is, as I mentioned, it allows us to use things a bit more dynamically. Typically, like a lot of people, I have previously used a fairly hard-coded kind of approach to doing microcontroller code. But been having a little bit more fun recently with allowing things to happen a bit more dynamically, making a bit more use of C++ and classes and things like that. And if done right, it really doesn't add that much overhead to either memory or CPU time in order to be able to do that. And it does add quite a lot more flexibility, especially when what we're aiming for as far as the F4, F7, H7, and F1 devices that we're going to be taking a look at, possibly also some F3 devices. It basically going to be looking at writing what is essentially a cut down OS for all of those devices, and in such a way that allows us to integrate those devices together to be able to have them work as a team and allow us to leverage some cool features that we may not be able to do otherwise, which is something I find quite a bit of fun. So with this one, as we've done a bit in some of our other videos with the Discovering STM32 series, we're going to be setting this up as a singleton class because we only want one timer manager to take care of all of the timers. So we're going to be setting this up in such a way that there can only be one of these classes, and means that we're going to have to do things a particular way, which I'll try and explain a bit as we go. Definitely recommend having a look at the Cherno's singleton C++ tutorial and a bunch of his C++ tutorials. He does some really good ones. Although I will also be doing a video on that coming up in future as well. So first things first with getting a singleton class done is we're going to be making our default constructor private so that it can't be accessed from outside of the class, which prevents multiple copies of the class from being created. And we'll just add some comments in here to help break this up as well. And we also want to delete the copy constructor and assignment operator as well, which we do like so. Make sure the stream's behaving, which it looks like it is. So basically taking that copy constructor and telling it to delete it, and same thing with our assignment operator. Like so. And the other thing that we're going to need to do to be able to get access to the class and to be able to allow it to work the way we need it to work is we're going to create a static get method that returns that returns a reference to the QAD timer manager itself. Now, the very first time that this method gets called, it will actually go through and call our default constructor. So anything that needs to be done in order to create the class will happen that very first time. And in here, we're going to create a static timer manager, and we'll call him instance. And because we've declared that as static, it's going to create basically the single instance of that. And then we're going to return that instance back like so. Now, what the singleton method does mean is that in order to get access to certain aspects of the class and different features and things within it, we will need to create a bunch of static methods to be able to do that. And then to be able to function within that class, those static methods will then need to call non-static methods that do a lot of our implementation for us. But again, I'll kind of show you a bit more of that as we go. So that's basically got our class set up a little bit to start off with. Now there's a couple of other bits and pieces that we're going to need in here as well. So we want to be able to, I'm going to create an enum to be able to identify which timer we're working with, which we're just going to call QAD timer perif. And in here, as I mentioned, we've got 8 different timers in this particular device, the F411 device. And we're doing this in the way we're doing it as well, because it'll make it more simpler to be able to port this stuff across to other devices as well, especially with the F7 device and the H7 devices that we've got coming up. There is a lot more timers in those devices than we've got in this one. So try and make this as flexible as possible. Now we also want to be able to put this last one in here to, might want to tell it what data type we're using there. There we go. So we want to be able to select any one of the 8 timers. And the particular timers that we've got in this device is 1 through to 5 and then 9 through to 11. Timer 2 and timer 5 are 32-bit timers, whereas all of the others are 16-bit timers. But we also want to be able to basically request from the manager if a particular timer is available, and we need it to be able to either return an identifier for the timer or none if there is no timer available, which is why we're putting the QAD timer none in there. That also gives us another little bit of a benefit in the sense that we also want a constant that we can use to tell us how many actual timers we have in this device. And again, this is something that makes it a little bit more portable when we go to port this between devices as well. So we can actually use timer none, which will be given the value 8. We can use that as the particular number for the amount of timer peripherals that we have. So it's kind of serving 2 different functions there. Now, we're also going to want might just pop a couple of comments in here as well, just to help break this up a little bit. I think I've had too much coffee this evening, but it should help us get this done, which is a bit of a benefit. So going to create another enum in here so that the manager can keep track of what each timer is actually being used for at the time, whether it's not being used or whether it's being used for a specific purpose. Part of the reason we want to do that is so that when things get a bit more advanced, we'll be able to go in to, say, a console connected via serial from the computer or other methods, and actually ask the system, you know, how many timers are being used for PWM, how many are being used for encoders, how many are not being used, things like that, and then it will actually be able to go through and check and return that as requested. So now going to make unused a 0, because that way we can easily check whether it's being used or not, because if it's not being used, it's going to be a Boolean false. If it is being used, regardless of what it is being used for, it's going to return a Boolean true. So sort of makes that a little bit more flexible as well. And we're just going to pop in a few. There will be more different uses that we're going to be popping in over time, but we'll just go with a few that are upcoming for the moment. one of the other uses which I'm popping in here is ADC. So we will be using timers when we go to do our stream or video on analog to digital converters as well. Timers are really handy in that instance because they can regularly trigger the ADC to be able to perform a conversion at regular intervals. Now we're also going to create an enum for the particular type of timer, whether it's 16 or 32-bit. And some of this stuff may seem a little bit overkill initially, but is going to make life so much easier when it comes to getting a lot more advanced with the timers and the system in general. So that's that one there. And then we also want to create a structure to be able to hold a specific set of information for each timer, so that we can then create an array of those structures so that we can store a full set of information for each of the 8 timers. It does mean that we're using up a little bit of memory doing that for information that allows us to track everything, but the trade-off of that is allowing us to more dynamically use the timers, which, considering we're not using that much memory to be able to do it, I think is a good trade-off to make. So just to separate things out a little bit more, let's pop one of those guys in there. And call this QAD timer data. And this will just be a normal structure. Like so. So firstly, we want to be able to keep track of what the timer's ID is, so that when we go to search for an unused timer with a specific set of features, it is more easily able to return that particular enum value. So that's that one there. We want to know what state the timer's in, whether it's being used or not, and what it's being used for, if it is being used. We're also going to keep track of what the clock speed of the particular timer is, even though for this particular device, all of the timers are effectively running at 100 megahertz based on how we've set the clocks up. So we've got our 2 different buses that some timers on one bus, some timers on the other bus. There's 4 on each. And one of the buses is running at 100 megahertz, whereas the other is running at 50 megahertz, but then that's being clock doubled. So effectively, all 8 timers are effectively running at 100 megahertz. But again, just to make life a bit easier, when we go to port this across, we will track that as well. And that also allows us to dynamically calculate things like if we want a timer to iterate at a particular period, then we can use that clock speed value, retrieve that from the manager, and use that to calculate what our prescaler and our period needs to be for that particular timer. So we also want to know how many channels are available on each of the timers. So off the top of my head, for this device, timers 1 through 5 all have 4 channels. I think 9 and 10 have 2 channels each, and then 11 has 1 channel. And that sort of allows different timers to be used in different ways as well. So such as if we're doing PWM, if we're using timer 2, for example, with 4 channels, we can do 4 separate channels of PWM with that. However, if we were using timer 11, we can only do 1 because there's only 1 channel available. So that way we can dynamically check that stuff as well. And we want to know whether or not a particular timer supports encoders, because not all of them do. So that's why we'll pop that one in there. And to make initializing things a little bit easier, we'll also store a pointer to the particular instance of the timer and what its associated IRQ is as well. In this case, we're just storing the particular IRQ for timer updates, which we're going to be using during the next stream, coming not long after this one. A couple of the other things we're going to be doing with timers will also be coming over the course of the next 4 or 5 days, I'm guessing. Hoping to be putting it out, another 4 streams or videos after today over the course of the next 3 or 4 days, depending on how we go. Hopefully make up for the fact that I was sick there for nearly a week. I do like the idea of getting videos out consistently because I do quite enjoy doing them. So in here, we're just going to create our array of timer data. Just call that MS timers, and we can just use our QAD timer perif count there to set our number for our arrays. Now, we might get our constructor done first. This is a bit of stuff that's going to need to go into that one. So let's get our CPP file ready to go. Forgot to update that bit there, and also forgot the date as well. Let's get that fixed up. Grab that. Pop this over. Yep. There we go. So this will be CPP. Get rid of our prevent recursive inclusion, and we want to include our QAD timer manager header file. And then we can grab our constructor, pop him over here. Pop in some comments to help break things up a little bit. And keeping things consistent with how we've been laying it out previously as well. All right. So a few things that we're going to need to set up here. So we basically want to go through and set up all of our timer data in the constructor, so that's ready to be used, and we're only going to have to do all of this stuff once. So a few bits and pieces we're going to do first up. Might help if I hit the right keys on the keyboard. It should be perif count. So we want to set the state of all of them to unused. And we're also going to set our encoder support data in here as well. So basically timers 1 through to 5 all support rotary encoders, whereas 9, 10, and 11 don't. So easiest way to fill this one out will be if I is less than QAD timer 9, it'll be a true, otherwise it'll be a false. We'll set our timer peripheral IDs. And I'm just going to copy and paste this. Go through and pop in the numbers for these. And that should be 11. Make sure they all line up nicely. to make life a little bit easier, let's, so you don't have to sit there and watch me type all of this stuff. For our clock speeds, timer 1, 9, 10, and 11 are all on our second peripheral bus. So just getting the HAL to return the particular frequency for those. So that bus is running on 100 megahertz. Our peripheral bus 1 is running at 50 megahertz. And so we're just multiplying that by 2 because, like I said, there is in the internals of the F411, with how we've got it set up, it is clock doubling that 50 megahertz as well. We also want to set up what the timer types are, whether they're 16 or 32-bit. And as mentioned, timer 2 and timer 5 are 32-bit. All the other ones are 16-bit. So setting all of that up there. Want to set up how many channels there are for each of them. So 4 channels for timers 1 through to 5, 2 channels for timer 9, and 1 channel for each 10 and 11. We'll set up our instances, which we'll use when we're initializing the timers, so that we've got those easily accessible. And same for our IRQs. Now, as mentioned, these are IRQs that are used for when the timer updates. So basically when its counter gets to the end of the particular period value that we supply it with. That's the particular IRQ that we can call there. And some of these are actually shared. So timer 1 shares its update IRQ with timer 10, as we can see there. Timer 9's update IRQ is also shared with the timer 1 break IRQ. And timer 11 shares its update IRQ with the timer 1 trigger, and can't remember off the top of my head what COM is, but basically 2 of the timer 1 IRQs are shared with the timer 11 update IRQ. So that's all we need to set up in our constructor there, and that basically gives us a full set of data to work with so that we can retrieve any of that as needed to be able to set up the timers and manage things a little bit more effectively. Now, we want to also be able to retrieve particular bits of information from our other drivers so that they can effectively check different things about the timer and get the bits of information like its instance or its IRQ in order to be able to initialize it correctly. So let's go through and get some of our data methods in here. And we're going to need to do kind of 2 sets of these. So we'll need to do the static version, which is accessed as part of the singleton class. And then we're also going to pop a private section down here where we're going to put the implementations for some of our other methods. However, with our data methods, because we're pulling that data directly from the array of structures that we've created, we don't need to double those up as we will with some of the other methods we're going to pop in here. So firstly, we want to be able to retrieve what state a particular timer is in. So for that, just use our get method. Because our static method can't see our non-static data, so we use our get method in order to retrieve our timer instance. And that then allows us to access the timer data from there. So for that one, and then we'll use eTimer as the index into the array. And the benefit of using the enum to be able to index into the array means that we're never going to be able to supply it with an index that is outside of the array. So it also adds that little bit of safety as well, which is good. Now, just create a few different ones of these. So we want one to retrieve the clock speed. Again, pass this the peripheral enum. And this will be for clock speed. We want what type of timer it is, so whether it's 32 or 16-bit. So that will be our type. To do how many channels we've got for each timer. So that will be channels. We want to be able to retrieve whether or not it supports encoders. Now, I could copy and paste and modify some of this stuff and make it a little bit simpler, but in situations where I can almost type it as quickly as it would be for me to copy and paste and modify the different bits, I'd almost just rather type it. Find it's a little bit easier that way. So that'll be that one. We'll be able to retrieve the particular HAL instance for each of them. Which will be our pointer to our instance. Just double check. Okay, good. I did put that down as a pointer for that one. And our IRQ as well. Let's call this get update IRQ, so that if we do get the manager to supply us with multiple different IRQs, we can separate those out. I like to sort of do things a little bit in a way so that if I do want to add features that I may use down the road, makes it a little bit easier to do so rather than having to go through and rename a bunch of stuff. And this will be missing an S there. And our IRQ. So that's those guys done so that we can retrieve the different bits of information as needed. We're going to create a couple of different management methods so that we can register whether we want to use a timer, so that when it's registered, we tell it what we're using it for. It keeps track of that so that we can't, prevents us from being able to go through and say if we were using a particular timer for an encoder, and then we went to try and use that same timer for PWM. When we go to check that with the manager and try and register that one, it's going, you can't do that because that time is already in use. And that helps prevent situations where if we'd initialized a timer for an encoder, then if we were then to go and reinitialize it for our PWM, then all of a sudden our encoder is going to stop working. So by using the manager, that does prevent all of that stuff from happening, which is definitely beneficial in a situation where we want things to be a little more dynamic. So this one will return a QA result, and we'll pass it which timer we want to try and register and what we're going to be using it for, which we'll just use our timer state enum for that. And then we can just go get, we'll call this imp register timer. So we haven't actually defined this particular method yet, but the imp register timer will be the non-static method that we will use to access the data inside of the class, while the static method is the one that gives us access to the singleton class from outside the class. Hopefully that makes sense. So we'll pass that e-timer and the e-state. And then we also want static void to deregister timer. So once we're finished using it, we'll then deregister it, so that then if we want to use it for another purpose, we can go ahead and do so. And only need to pass that which timer we're deregistering. Nope, don't need to pass it anything else. And we also will pop in a method to be able to find a particular timer. So say if we've got a few timers set up, and then we go, okay, I want a timer that is capable of supporting an encoder, as an example, then we can use this particular method to be able to find a timer that's going to support the particular features that we're looking for that is not currently being used. So we're going to pop a couple of bits in here. So one to allow us to select whether we want a 16 or 32-bit timer, and then another one to be able to tell it whether or not we want to try and find a timer that's available that has encoder support. So that should be timer type, and then whether or not we require it to have encoder support. Just call that imp find timer and pass that e-type and b encoder. Then a couple of other methods that we're going to want as well. So as far as with the clocks, so to enable the clock for a particular timer, we need to call the HAL RCC method for that. And because there's a few different methods, rather than having to create a big switch statement in the initialization for each of our different drivers, we're actually going to create a couple of methods in our manager to be able to do that for us, so that we can then just reuse that code from the manager, and keeps that nice and neat and all in one place as well. So that will be timer perf, timer, and again these guys will be calling the implementation methods in order to be able to undertake that as well as part of our singleton class. And we also want a couple of status methods. We're only going to create a couple for the moment. We might add some more later, but we're going to have one to be able to check how many timers are currently being used and how many timers are currently available. We'll also come back at a later date and add some to find out how many are being used for encoders, how many are being used for PWM, things like that as well. But for the moment, we're just going to go with how many are active and how many are inactive. And this stuff will be really quite useful, especially when we're using, say, one of the H7 devices where it has an absolutely crazy amount of timers. I think there's like 18 or more in a particular H7 Nucleo board that we'll be looking at in future. Alright, now for our management methods, clock methods, and status methods, we also need to declare our implementation methods. So this will be returning a QA result. And that will be imp register timer and QAD timer ref, timer, and QAD timer state and e state, like so. These will just be declarations because we'll be putting the actual code for these guys in the CPP file. I keep the code for the static methods in the header in the class declaration, simply because there's only one line for each of them, and I do find it helps keep things a little bit separated in between the actual static singleton methods and our actual implementation methods. It could do it either way, it's just the way I prefer to do it. Okay, and we want for a timer, and we want to pass that QAD timer type and a boolean to let it know whether or not we need encoder support. So do our clock methods, which don't need to return anything. Might just copy and paste that one. So they're both pretty similar. And we'll do our status methods as well. And that will be imp get timers active, which we don't need to pass anything to. Like so. Copy these guys over to our CPP file. And let's get these guys ready to go. Again, keeping everything consistent with how we've been doing our code across the board. Making sure that everything stays consistent, so regardless of whether, if you download the F7 discovery code from GitHub, or this F4 Nucleo code, or the H7 Nucleo code. It's all going to look fairly similar and make it nice and easy for people to be able to navigate regardless of which device they're getting the code for. Copy and paste this guy. Like so. Grab this one, pop that in there. This will be a clock method. And these will be status methods. It's that one. Deregister. And last but not least, our register timer. All right, let's get some code into those guys. So for this one, first up, before we actually try and register, we're going to check whether or not it's actually being used. And if it is, then we're going to return a fail. Actually, we might change that up a little bit. Let's jump in here, and we're actually going to start to add some more result values in here so that we can keep track of things a little bit better. So add two of them, which both will be used for our timers. So one will be proof busy if it's currently in use, and go with proof not supported, so that we can return that in a case where, say, we're trying to set up a timer for an encoder that doesn't actually have encoder support. And again, we will be adding more to this as we go. As part of our actual operating system, as we go ahead and build that, we will be making it so that we have an actual error manager that handles all of that stuff and allows things to happen a bit more gracefully, while also giving us a nice bit of detail about the particular errors that are occurring. So we'll pop those in there for the moment, and in this case, we're just going to return perif busy error. There we go. Now, if it's not currently being used, then we are going to change the state of that timer to the state that's being supplied here, which will then keep track of what that time is being used for. And then at that point, we can just return QA-OK to let it know that we've successfully registered that timer. In this instance, for deregistering, we basically just want to set our state for the moment to not being used. Fix that indent up. And then as far as finding a particular timer, we're just going to do a bit of a for loop to iterate through the timers. If we get to the end of the for loop and it hasn't found one, then we'll return QAD timer none. And in here, we're first going to check if we are getting the correct type. I'm going to do it this way because effectively the 32-bit timers also have 16-bit support. So if we're looking for a 16-bit timer, then we can use any of the 8 timers. However, if we want a 32-bit timer, then we specifically need to retrieve one of the 2 32-bit timers for this device. And because we've set the enum up so that the value of 16-bit is less than 32-bit, we go up to here, so 16-bit is equal to 0, which would then make this one equal to 1. We can just go, if eType in here is less than or equal to the particular type for that timer, then we know that it's going to support what we're looking for. And as far as our encoder support, if we want one that has encoder support, then we need to check whether or not the one that we're iterating through actually supports encoders. And otherwise, if we're not after encoder support, then we can just do that as well. So basically, it either needs to probably even just do that as well, tidy that up a bit. So it either needs to have, if we are after encoder support and it supports encoders, or if we're not after encoder support, then we're good to go. And in that case, if it supports everything we want, then we'll just return what its actual enum value is for that particular timer. Now for these guys, because we can't just really create an easy array of our clock enable and clock disable functions using the HAL, we're going to use a switch statement in here to be able to do it for the particular timer that we're looking for. So just going to pop one of these in here and then we shall copy and paste. Timer 1 clock enable and break. 4, 5, 6, 7, 8. Timer 2, timer 3, 4, 5, 9, 10, and 11. Now doing our disabling of our clocks is going to be fairly similar. We also need to do a case for timer none, otherwise we will get the compiler whinging at us about that. We don't even really need to put a break in there for that one. Just as long as we put a case in there for that one, it'll keep the compiler happy. So let's copy this into here. And then we're just going to do a find and replace on this one. For enable, we're just going to change that to disable. That's that one done. And then just our methods to find out how many timers are active and how many are not active. So for this one, create a variable just to keep track of this, and then do a for loop. If ms timers the state, so if the state is 1 or above, or a boolean true, because of how we set up the enum, then it's being used. If it's a boolean false or a 0, then it's being not being used. So it makes it easy to be able to do the if statement for that one. And if it's being used, then we'll just increment the count, and then at the end of that, we're just going to return new count, which is the amount that are currently being used. And do a similar thing for this one. In fact, we might just copy and paste this like so. And in this case, we're just going to check, invert that guy, so that it's going to check basically which ones are false. And that is basically our timer manager all ready to go. As mentioned, in the next stream coming up, we're going to be looking at doing our timer update IRQs. So do a driver to be able to set up a timer to do trigger an interrupt request at specific intervals. We'll do it so that it can be done continuously, or say if we just wanted 10 updates and then for it to stop, or just a single one, things like that, then we'll add all of that in there. And when we do that, we'll get to see how that interacts with the timer manager. And as mentioned earlier on, we also will be doing some videos coming up over the coming days for setting up encoders, pulse width modulation. I think the next one I'm going to do after that will be the analog to digital converter, where we'll also be using timers there as well, because we'll be using the timer to trigger the analog to digital conversions at a specific time. So we'll get to see how we can use timers to internally trigger other peripherals inside the STM32. You can also use timers to trigger other timers as well, which is kind of adds quite a lot of flexibility to what you can do with the timers. I think they're probably the most flexible peripheral in the STM32 devices. So that's our timer manager. Hope you found that one interesting, and I will be back streaming probably half an hour after this stream ends to do the timer update IRQ driver. And if you like this one, would love it if you followed us on Twitch. If you're watching on YouTube, love it if you liked and subscribed. Got any questions or want me to go into a bit more depth with anything that we've covered during this video, definitely leave a comment either on YouTube or Twitch, or jump onto our subreddit r/ones and zeros. If you want to help out with some of the videos coming up, because there's a lot of videos that I've got planned. I think there's 7 more videos that I've already got the preparation work done for already. And there's probably several hundred videos that are on my list that I want to get done over the coming months. So if you want to help out with that, I'd love it if you jumped on Patreon and gave us a bit of support there. There is some bonuses that you can get with Patreon, including when we get into some of the more advanced code that will be accessible to Patreon members only, whereas a lot of this more basic stuff that we're doing at the moment is going to be available to anyone on GitHub. So thank you so much for watching. Hope you have a great night, day, morning, night, whatever it is where you are. See you next time.